Okay, hello everyone. In the beginning of the part 3 of today's class, let us see new announcements. Okay. So the first new announcement is the slides of chapter 2 has been updated. Version 2022-0531B. Hello everyone, I have uploaded the latest version of slides of chapter 2 to eCourse2 website. The location and the file name are eCourse2 website, wireless communications and machine learning, course content, slides, chapter 2 slides 2022-0531B.pdf. Best regards, Wei Zhen. Okay, the second new announcement is the handout of chapter 2 has been updated. Version 2022-0601. Hello everyone. I have uploaded the latest version of the handout of chapter 2 to eCourse2 website. The location and the file name are eCourse2 website, wireless communications and machine learning, course content, handouts, chapter 2 handout 2022-0601.pdf. Best regards, Wei Zhen. Okay, so let us continue the class progress. Okay. So in the second part of today's class, we have taught to this reference. Okay. This is a report which was written by Byte Mobile. The title of the report is Mobile Analytica Report, and which was published in June 2011. Okay, let us go back to the slide. Okay, here. The video sequences used were flower vase. Okay, what is a vase? Let us see the handout. Okay, so let's search for vase. Okay, problem 3. What is a vase? Solution: a container for holding flowers or for decoration. Okay, let us go back to the slides. And race horses at 30 frames per second FPS and resolution 480p, while for resolution 360p, tennis and park scene at 24 FPS were selected. Okay, as a result, it was observed that a function of the form PSNR is equal to K times log RIS plus P can be used to very closely approximate the average PSNR bit rate. Bit rate is the term RIS curve, where K is equal to 10.4 and P is equal to negative 28.7221 are constants. Next, to obtain the parameters of the logistic function in equation 2.17. Okay, let us see equation 2.17. Okay, we can see that in equation 2.17, okay, QV, where QV denotes the MOS for video, is equal to C over 1 plus exponential of d times PSNR minus f. Okay. C, D, and F are the parameters of the logistic function. Okay, let us go back to not here. Okay, here we computed PSNR values using the PSNR bitrate curve for bit rates obtained from equation 2.15. Okay, let us see equation 2.15. Okay, in equation 2.15, when using AMC, okay, that is adaptive modulation and coding, from Chu and Tralla, 1999, the relation between transmit bit rate and the secondary user threshold SINR is RIS is the transmit bit rate, is equal to W, which is the channel bandwidth, times log 2 1 plus K, okay, times beta IS, where beta IS is the secondary user threshold SINR. Oh, sorry, I should introduce K first. K is equal to 1.5 over negative natural log 5 times BER, is a constant that depends on a target maximum transmit bit error rate BER requirement. Okay, let us go back. Okay, equation 2.15 for all candidate resource allocation actions. To get the MOS values that correspond to the computed PSNR values, we used the average of the linear mapping in figure 2.2. Okay, let us see figure 2.2. Okay, this figure, MOS versus PSNR. Okay, I have introduced it to you earlier in today's class. Okay, and the conversion in table 2.1. Okay, let us see table 2.1. Okay, table 2.1 is the PSNR to MOS conversion from Piamrat et al. 2009. Okay, I also introduced this table to you earlier in today's class. Okay, after obtaining the MOS PSNR pairs, the resulting parameters in equation 2.17. Okay, let us go to equation 2.17. Okay, this equation, okay, I have introduced it to you several minutes ago. Okay, go back. Where C is equal to 6.6431, D is equal to negative 0.1344, and F is equal to 30.4264. In the present case, following the user-centric approach. Okay, what is the user-centric approach? Okay, that is an approach which treats users as center. Each secondary user will perform resource allocation aimed at maximizing its QAE. Okay, what does aimed at mean? Okay, it means that we take the maximizing QoE as our goal, okay, or purpose, measured as MOS for all traffic types. For the reasons discussed earlier, resource allocation is done through a Q-learning process. However, in order to reduce the convergence time, in this case we will follow a DQN approach instead of table-based Q-learning. Okay, We have introduced what is a DQN. Okay, if you forget, okay, you can search for this DQN. Okay, so in page 49, we have introduced what is a DQN. Okay, a deep Q network DQN is an emerging class of deep reinforcement learning algorithms that is capable of combining the process of RL, okay, that is reinforcement learning, with a class of neural networks. Okay, we have introduced what are neural networks in chapter 1. Okay, if you forget, please review the handout of chapter 1, known as deep neural networks, to approximate the action value function. Okay, so we have also introduced what is the Q-learning. Okay, if you forget, please review the handout of chapter 2. Okay, so one of the disadvantage of Q-learning is about the long convergence time. Okay, so in order to reduce the convergence time, we will use a DQN approach instead of Q-learning. Okay, nevertheless, okay, we have introduced what is the meaning of nevertheless. If you forget, please review the handout of chapter 2. As in any Q-learning process, we first need to define the state space, action space, and the cost or reward function. Because the network setup has not changed from the previous section, the states are still defined as ST, which is equal to IITLT. Okay, do you remember this? Following equations 2.9 and 2.8. Okay, let us go to equations 2.9 and 2.8. Okay, in equation 2.9, LT is equal to 0 if gamma 0 TP is greater than or equal to gamma 0, and LT is equal to 1 otherwise, where gamma 0 TP and is given in equation 2.1. Okay, let us go to equation 2.1. Okay, in equation 2.1, we can see that gamma 0p is the signal to interference plus noise ratio SINR of the primary user. Okay, so here gamma 0 TP is the SNR of the primary user at time t. Okay, and what is gamma 0? Let us go to equation 2.1 again. Okay, gamma 0 is here. Gamma 0 is the primary user's required SINR threshold as determined from the underlay DSA configuration. Okay, DSA means the dynamic spectrum axis. Okay, and in equation 2.8, IIT is equal to 0 if gamma ITS is greater than or equal to gamma I. IIT is equal to 1 otherwise. Okay, where gamma ITS is given in equation 2.2. Okay, let us see gamma IS for secondary user I, the corresponding SINR is gamma IS. Okay, so we can know that gamma ITS is the SINR of the ith secondary user at time t. Okay, and what is gamma I? Let us go to equation 2.2. again. Okay, gamma I is here. Gamma I is secondary user I's required SINR threshold determined from quality of service QoS goals. Okay, so let us go back to here. Good. Since the goal now is to maximize MOS, the Q-learning process is designed with a reward given by rho IT is equal is equal to M if LT plus IIT is greater than 0, and rho IT is equal to QDI or QVI otherwise, where M is a constant smaller than the minimum MOS. Okay. So what does this equation mean? LT plus IIT is greater than 0. Okay, let us go back to equations 2.9 and 2.8. Okay, we can see that IIT is equal to 0 or 1, and LT is also equal to 0 and 1. Okay, so when IIT plus LT is greater than 0, it means that at least one of them is equal to 1. Okay, right? Okay. So what does it mean 1? Okay. Otherwise 1. Okay, what does this mean? Okay, it means that gamma ITS is smaller than gamma I, or gamma 0 TP is smaller than gamma 0. Okay. So this phenomenon we call it as outage. Okay, SINR is smaller than the threshold. Okay, so if at least one user is in outage, okay, then LT plus IIT is greater than 0. So we assign the M to rho IT. Okay, so we can see that rho IT is a reward, the reward of the ith user at time t. Okay, so if any user is in outage, okay, then we give M to the reward. Is a constant smaller than the minima of MOS. Okay, and do you remember what is the minimum of MOS? Okay, let us review it. Okay, we can see that the minimum of MOS is equal to 1. So the outage is a worse condition than the bad. Okay. Okay, as can be seen, the MOS for either video QV. Okay, so now you know why we use V here, because it means the quality of video V, or data QD. Okay, so similarly, now you know why we use D here, because it means the quality of data D. Okay, traffic is the reward obtained when satisfying the interference constraints. Okay, that is SINR should be greater than or equal to the threshold, and is sent from the secondary user receiver to its transmitter through the AMC. Okay, that is adaptive modulation and coding feedback channel. Okay, what is a feedback channel? A feedback channel is a channel which can transmit some information from the receiver back to the transmitter. Okay, it is called the feedback channel. Finally, for the action space, each secondary user conducts a search into the finite discrete space of candidate target SINRs. Okay, so a set A is equal to gamma 1I to gamma Ni. Okay, So there are totally small n candidate target SINRs for the ith secondary user. For the ith user. Okay. At the same time, when choosing one strategy from A, okay, this set. Okay, so we have small n choices that we can choose from. Okay, each secondary user adapts its transmit power as well as its modulation and channel coding rate. Okay, we have introduced what is the channel coding rate. Okay, if you forget, please review the handout of chapter 2, which in turn determines RIS. Okay, that is the transmit bit rate. Okay, as previously indicated, in the DQN approach, a function estimator is used to estimate the optimal action value function, with a neural network being used as an efficient nonlinear approximator to estimate action value function Qi of Si ai theta I. Okay, so Qi is the action value function. Okay, that is a Q function of the ith user, and Si is the state of the ith user, and Ai is the action of the ith user, and theta I is the parameter of the ith user. Okay, so it is approximately to Qi star of SIAI. Okay, when you see a symbol star here, it means the optimal value or optimal function. So we are going to choose a theta I to optimize the value of function Qi. Okay, please see Mini et al. 2015. Okay, let us see this reference. Okay, so here Mini et al. Okay, have wrote a paper. Okay, human level control through deep reinforcement learning, which was published in Nature. Okay, this is a very good journal in 2015. Okay, so where the notation of the bivariate function Qi of SIAI theta I. Okay, what is a bivariate function? It means that this function has two variables. So here the two variables are Si and Ai. Okay, has now been expanded to include the parameters, that is the internal weights theta I of the neural network, which was designed as a fully connected feed-forward multi-layer perceptron MLP network. Okay, what is a multi-layer perceptron? Okay, before introducing what is multi-layer perceptron, we need to know what is perceptron first. Okay, so please look at the handout. So page 71, problem 1. What is a perceptron? Okay, solution. In machine learning, the perceptron is an algorithm for supervised learning of binary classifiers. Okay, what is supervised learning? We have introduced it in chapter 1. If you forget it, please review the handout of chapter 1. Okay, then what is a binary classifier? Okay, a binary classifier is a function. Okay, it is 25 minutes. Okay, see you next time. Goodbye.